Hello. Or he's not loud at all. Hold on. I had it muted. I was protecting.
Yeah, it'd help if you didn't mute.
I was just protecting. That's all.
Protecting? What were you protecting? Our ears? Our sensibilities?
Oh, sorry. I muted my own. Yeah, I was protecting everybody.
Everybody. No one wants to hear what I have to say.
Heavy breathing into the mic.
Oh, this.
Oh my God. I didn't do that. Oh God. Oh God.
You said it. You said it.
I did not.
You literally said it.
No. Okay, I have to adjust this. So, guys, here's Dr. Paul.
Hi.
So I have a question for you.
All right, let's do it.
Does Apollo 1 count in the Apollo missions?
It's number 1. Sure.
Does it count? Would you call it an Apollo mission?
Sure. Why not? It's literally Apollo mission number 1.
Right. Okay. Just making sure.
It's defined to be.
Right. Okay. Just checking. That's how I started my stream.
What's the controversy? What's the controversy?
I don't even know. Maybe that people died and people don't like it when people die. I don't know.
Yeah, it's horrible.
Yeah.
And it ended in failure.
Mm-hmm.
And tragedy.
Mm-hmm.
But it was still a mission.
Yeah. There was a lot learned from it. Yeah. Yeah. Can everybody hear him okay? Everybody can hear Dr. Paul okay? Enough?
Nah, no one cares.
Yep. Okay, good.
Yeah, whatevs.
Nice. Good. I didn't want to see. The only thing is with Zoom, I don't have that control. Zoom seems to always do that bing ding. No matter if you mute it.
Oh, that thing. Yeah, it doesn't matter.
Yeah.
Boom, boom.
It's so annoying. It's so annoying. Yeah. So how was your weekend? How was everything?
It was a good weekend. It's freezing cold here.
Mm-hmm. Same
I think
here.
it's gonna be 1 tomorrow.
Ooh.
Which sucks. Yeah. That's nippy.
Yeah. Yeah. I think everybody's saying that too.
And it's not a day where I can just stay inside and be cozy. It's a run around town day. So not looking forward to that.
Yeah.
But just otherwise just keep on keeping on. Living the dream.
Living the dream. And we just watched actually your the victory over Antimatter.
Oh yeah.
And there was a good question that came up, but I wanted to save it for you. And
well, let's do it.
Yeah, someone asked if there's any way that we know that there's not just missing antimatter that we haven't found yet. Are we pretty definitive on our claim that there's no more antimatter?
Right. So we've looked really hard in 2 ways. One is we've looked out in the universe, like, hey, is there a galaxy made of antimatter floating around? And we don't see it because galaxies aren't totally isolated. There's always stuff falling into galaxies, just material from intergalactic space. And so if that material was normal matter hitting anything in the antimatter galaxy, it'd go boom right away. So we don't see that. So as far as we can tell, all the matter that we see in the universe is normal matter. And then the other way is through our understanding of the physics of the very early universe, that if there was a lot of antimatter still flowing around and every once in a while interacting with normal matter, that would change the evolution of the very early part of the universe, and we would get different looking universe than we do today.
Ooh, someone says, could dark matter be antimatter?
Right. So if dark matter were antimatter, the entire universe would blow up in an instant.
Why?
Because all the dark matter it's infused in the galaxy. So if you look at a galaxy, it's really embedded in a halo of dark matter. And so if that dark matter were antimatter, then the antimatter would be interacting with that normal matter and it would go pop.
Oh. So yeah. that's a good thing. That's a good thing. That we don't.
So antimatter and matter, when they collide, it is 100% pure mass to energy conversion.
Mm-hmm.
Like it is the most efficient way of generating energy out of colliding particles, out of any interaction. So like I forget the exact numbers, but like a thimble full of antimatter could blow up the Earth. or something ridiculous like that. So if you imagine a galaxy of matter colliding with a galaxy of antimatter, it's bad news.
Bad news. There you go.
Bad news bears.
Yeah, but that's actually a really good question, Igorog. That was actually a really good question.
Because there's all sorts of weird matters.
Yeah, right.
In the universe. Yeah.
And usually I'm waiting for someone to be like, so what about dark energy?
What about dark energy?
Well, what do we know about dark energy? Yeah, I'm going to ask you, what do we know about dark energy, Dr. Paul?
We got nothing about dark energy. We don't know. All we know is that our expansion of the universe is accelerating.
Mm-hmm.
It's getting faster and faster every day. That's it. That's all we got, folks.
That's it.
It's been 20 years since we discovered it.
It's been 20 years. Let's up the game.
It was discovered.
Ooh.
Yeah. We need more money.
Wait, it says, so could a white hole have made the excess matter of Ludriel?
just throwing in all the jargon words. White holes don't exist.
Go on.
White holes don't exist in the universe, and excess matter is different. It's a whole different ballgame.
Can you repeat that first part again?
White holes don't exist.
What about wormholes, though?
Wormholes don't exist.
What do we have with wormholes? Do we have the mathematics behind them?
We have the mathematics behind them, and we know exactly how to construct one. If you want to build a stable wormhole that you could actually travel down, it needs to be made out of material with negative mass.
Oh, where do we find that?
We don't.
Oh, yikes.
Yeah, because that's not a thing. It just isn't. Negative mass doesn't exist in our universe.
Yeah?
So without negative mass, you can't get wormholes and you're done.
Well, negative mass sounds really cool, though.
That's your opinion.
You don't think that sounds like one of those heavy metal bands ever?
Negative mass?
Yeah. It's simple.
It sounds like one of those Japanese metal bands.
Negative mass is like Cosmic Spanx.
Yeah. Exactly.
And thank you everybody that's coming in with the resubs. Thank you. I will get to those after. I don't want to interrupt Dr. Paul in his time because he takes time out of his day to hang out with us here.
That's right.
Yeah.
I'm very valuable.
He's super busy. Are you still filming?
So busy, man. I just got up from a nap.
Well, are you still doing, are you still like filming how the universe works, or is that already done and now they're just showing it?
That was filmed last summer. And so it's showing, they're doing the season run. I think they have a couple more episodes left, or a few. I don't know.
And then
I don't have cable,
they're going to start filming again in next summer?
Yeah, well, hopefully. So it's every year, like they run, they check the ratings, and then Science Channel buys a new season if they want to keep going. And so if they want to keep going, Science Channel buys a new season, the producers get to work, we figure out schedules. Sometime during the summer I film, and then it repeats.
There's negative mass. No, Justin, there's not. No, we're just...
No, negative on the negative mass, and that's not a double negative.
That does not make a positive.
Just negative mass.
So Scud has a question. I got a theory that answers all three of these things. Shoot me down, Dr. Paul. Shoot me down, Dr. Paul. He said that.
Shoot me down. That sounds like a song. Shoot me down, Dr. Paul.
In the 80s.
Yes, very 80s song.
The Big Bang was balanced, and the antimatter is beyond the observable edge of our universe. And being antimatter is gravity repels normal matter, which is A, why it and matter clump separately. B is the inward push that dark matter is blamed for. And C is its expansion away from the matter means the gravitational repulsion is getting weaker, hence the dark energy acceleration of the universe.
Antimatter, you asked to be shot down, so here it goes. No mercy. Antimatter has normal gravitational attraction. If I have a ball of antimatter or a planet made of antimatter, I can orbit around it just fine. It has totally normal gravity. It's not repulsive. It is. It has opposite electric charge. That's it. That's it. Just opposite electric charge. Everything else about antimatter is totally normal.
Okay.
I'm done. I'm done.
You're done with that one? Okay.
That's all I need.
Well, there's so many other good questions that are coming in. Okay, so
Let's hit it.
What about tachyons?
What about tachyons also don't exist?
Don't exist.
Just stop.
Wasn't there a theory where insanely tiny wormholes exist at the scale of the quantum foam?
Yeah, I mean, the quantum foam is all sorts of weird business, and
I want a quantum foam bed. Quantum foam mattress.
Way better than memory foam. So expensive, though. So expensive. They make it in Switzerland,
Ooh.
and they only export like 500 a year. It's ridiculous. There's a waiting list. It's like harder to get that than a Tesla. It's just a joke.
It's very unique.
Quantum foam mattresses.
I want quantum foam mattress. Write it down, boys. I have a P.O. box. And so does Dr. Paul.
Yep.
So does
P.O.
Dr.
Box
Paul.
3322, Columbus, Ohio, 43210.
I don't know mine off.
Quantum foam.
Yeah, I don't know mine off the top of my head. So, no, wait, what is this quantum foam stuff? Is there a way you can summarize this for people that are like, wah?
Yeah, okay. So,
Me
quantum
included.
mechanics is all sorts of super weird.
Mm-hmm.
Down to very, very, very tiny scales, like super, super tiny. What we call the vacuum of space is really just this buzzing, bubbling, foaming froth of particles popping in and out of existence, of fields vibrating. This is the quantum field picture of reality. So if at very, very tiny scales, you have all this activity that's just kind of humming along and doing its thing in the background, then space-time will respond to that because space-time responds to the presence of matter and energy.
Right.
So if there's all sorts of buzzing, vibrating stuff, then space-time itself will be foamy at those scales. Maybe. We don't know because we don't know how space-time connects to the quantum world at those scales because that's quantum gravity, and we don't have quantum gravity.
Did that sum it up for, because that summed it up for me. I just want to make sure anybody else, if they have any questions on that. And let's see.
I'll wait.
I know. Well, okay. So what's quantum entanglement? Graham asks. And hi, Graham.
Quantum entanglement this is all the quantum words. We're just doing, it's like the buzzword review. It
is. It's something that I always tell people I am not qualified to get into. Like, we can watch things together, but as far as me being like, yeah, I'm going to get into some QM and really know what I'm talking about, nope, not going to even try it. Mm-mm.
All right. Let's say I use this analogy in my podcast. You and me
oh God,
are going to join a no, I'm not going to kill you this time.
Okay, thank God. All right.
We're going to join a Cheese of the Month club.
Okay, that's way better than you killing me.
Way better than falling into a black hole.
Yep.
So the Cheese of the Month club, you just get sent a random cheese.
Okay.
And but this isn't a normal Cheese of the Month club. It's a quantum Cheese of the Month club.
So I get quantum Gouda. Smoked.
Well, you don't know what you're going to get.
Oh, no.
Okay, that'll be one of the options. Will be smoked Gouda.
Okay.
So what is they prepare 2 boxes of cheese.
Okay.
And there's 1 cheese in each box.
Uh-huh.
And there's just 2 kinds. One is smoked Gouda. What should our other kind be?
What's your favorite? One of your favorites?
I like a good Comté. Nice
okay,
French
well, bless you.
Cheese.
And we'll go with that.
Okay, so we got Comté and a smoked Gouda.
Okay. I'm ready.
They go in the boxes, and then the boxes are sealed up. 1 box gets sent to me, and 1 box gets sent to you.
Okay.
Because that's how the Quantum Cheese of the Month Club works.
Sounds fair.
So these cheeses are entangled. They were prepared at the facility to be entangled, which means they share a quantum state.
Right.
They are actually in a unique state all to themselves, even though they're physically separated.
Mm-hmm.
Okay, so far so good.
Mm-hmm.
I get my box, you get your box.
Okay.
I don't know what's in my box. You don't know what's in your box. Right?
Right.
Right. So I open up my box. And let's say I find smoked Gouda. Because our cheeses are entangled, I find smoked Gouda. I know for sure that you will get the Comté. For sure. And even though you haven't opened your box yet. You have not made a measurement. You have not made an observation. I know that you get the Comte.
Right. Great deduction.
Great deduction. In the same works in reverse. If you open up and you find the smoke Gouda, you know that I got the Comte. Or if you get the Comte, then I got the smoke Gouda.
Right.
I have knowledge of your cheese without visiting you.
Right.
I don't have to open up your box to know what you're going to find.
Right.
Because the cheeses are entangled.
Mm-hmm.
And what this means is that if I were to open up and I would find the Gouda, then I know you get the Comte. Then you go to open up and for sure you're going to get the Comte. If I opened up and got the Comte, then I know for sure you're getting the Gouda, so you open up and you find the Gouda.
Mm-hmm.
I know what you're going to measure. Just from making a measurement here in Columbus,
right,
I know what you're going to measure over in Colorado.
Okay.
And that is going to happen instantly. That choice is going to happen faster than the speed of light. We could open up at the exact same time, or as close to the exact same time as possible.
Mm-hmm.
And if I find the Gouda, boom, you've got the Comte.
That fast. Even faster than that. Way faster
Even
than that.
faster than
Way faster than that. Yeah.
This entanglement happens regardless of distance. You could be on the other side of the Milky Way galaxy. And I know for sure that when I open up and I get the Comte, that you've got the Gouda. I know for sure. Regardless of where you are in the universe, because because the two cheeses are entangled. Measurement on one affects measurement on the other. As soon as you measure one, you know the state of all the entangled partners.
Does that make sense to everybody? How do you know that the cheese factory didn't send 2 Goudas?
Good question. So in the game of entanglement, we're going to set it up so that it's either or, so that the cheese factory is only sending 1 Gouda and 1 Comte.
How do we know which ones are entangled?
Oh, yeah. So you actually have to be very careful to set up an entangled state. You have to bring 2 particles close together. You have to get them nice and cool, allow them to, mingle, have a couple drinks, and then they become entangled. And then you can very, very carefully separate them. You can also entangle photons, beams of light. You can tangle them together. So once they're entangled, you have to treat them very carefully to make sure you don't break that entanglement. But it can be done.
Yeah, Ludriel asks, but were they not already decided from the moment they left the factory?
This is something that really bugged a lot of people in early quantum physics, where it's like, did the factory know ahead of time which one I was gonna get? And for this analogy to work, the factory is just going to send out a random cheese. They don't know who's getting which one ahead of time. It is totally 100% random. Before I open my box, I have no idea. No one in the universe knows what cheese is inside that box. But as soon as I open it up and I'm like, okay, Gouda, then we all know that you've got the Comte. But until that observation, until that measurement happens, nobody knows. Nobody knows.
Sorry, I'm scrolling up to see some of this. Oh man, there's so many quantum questions.
Scroll.
I am. Did somebody say the Apollo missions from NASA? Yeah, this is yep. That's later. There were some other ones. Oh, Dodgy, yeah. So okay, well that's going back, but it's okay. It's okay, guys. We're not done with the quantum talk.
Cool.
I'm just
cool.
Yeah, we're just throwing
We're
questions.
taking a break. We're doing a breather.
So are there planets and stars made from antimatter just hanging out?
As far as we can tell, no. All the matter in our universe is normal matter. Because if you had a star and a planet orbiting it made of antimatter, it doesn't live in isolation. There's constantly stuff flowing in and out of solar systems, in and out of galaxies. There's all sorts of movement and activity. and that would trigger matter-antimatter annihilation, and it would blow up.
Do gravitons exist?
We don't know. We don't know. So gravitons are the if we had a quantum picture of gravity, then gravitons would be the thing that carries gravity from place to place.
Mm-hmm.
But our language of using particles like photons and gluons and gravitons to carry forces from place to place breaks down when we try to apply it to gravity. So we're not sure if the word graviton is even the right kind of language.
And would antimatter cause anti-gravity? Someone asked that earlier, and Vladi's asking now.
Normal gravity. Normal gravity.
Games and movies use tachyon enhanced communications. Someone says with the smiley face.
If we actually had to wait, 300 years from the communication from the home office, that's going to be a really long movie.
And so Dragon says this doesn't make logical sense though. With what? Okay, they don't know, but it was already decided. So yeah, we don't know until we get the box, right? But it was already decided who was going to get what.
There's no prior knowledge. There's no hidden variables. You don't know until you open the box.
No matter when or where you opened it, the outcome would have always been the same? ?
No, it'd be random. It'll be random. Like, I don't know. I'm going to open it up and it's going to be a Gouda or a Comté. It's 50-50 chance. The next month, it'll be another chance. They can send the exact same 2 cheeses and it'll be totally random chance. I don't know which one I'm going to get.
Does a red-shifting photon break the conservation of energy?
Right. So as a photon travels through our universe, the universe is expanding. The wavelength of that photon will stretch out because space underneath it is stretching out, and it will lose energy. So you might be wondering, well, where did that energy go? Because energy is supposed to be conserved. Energy is not conserved.
So yes.
Or it's more accurate to say conservation of energy is a thing, but when you apply it to a living, breathing, dynamical system like the expansion of the universe, there's different rules. The expansion of the universe can steal energy away from a photon.
Does antimatter fall up?
Antimatter falls down. The only anti in antimatter is the electric charge. That is it. Do you see the finality of my hand gesture?
Yes, I do. In superposition before you observe the cheese. So the cheese, is it in superposition before you observe the cheese? So the cheese can be in superposition and entangled at the same time?
Yes. Yes.
Why did normal matter win? We don't know, do we?
Well, one of them had to.
One of them, yeah, but we don't know why it was matter and not antimatter.
We don't know why it was one or the other, and one of the biggest mysteries right now, was something huge that we don't understand, is that almost all particle interactions, like 99.999% of all particle interactions, are perfectly symmetric between matter and antimatter. If you make a bit of matter, you'll make a bit of antimatter.
Okay.
But we ended up in our universe with a lot more of one than the other. We don't know why.
Isn't it true that matter and antimatter not only have different charges, but also different quantum numbers?
Matter and antimatter will have different charges, but charge here can be either electric charge or a weak isospin charge or nuclear or color charge. It's the word charge can mean more than electric charge. There's charges, quote unquote, for each of the fundamental forces, and you can flip any one of those to get antimatter.
Okay.
So they do have different quantum numbers. because they have different charges.
Alrighty. Can
Sure.
faster than light particles? We'll start there. Are there faster than light particles?
No.
Okay. So I think the answer to that is
no.
I'll finish the question.
No.
But what about the God particle?
The God particle, aka the Higgs boson, is it's a very special particle. Does a lot of cool stuff, but it's massive, travels slower than the speed of light.
There was some kind of mechanical failure as to why it gave incorrect readings, right?
For what?
Faulty wires or something with CERN.
Oh, that was so.
CERN.
This story. Oh my gosh, that was a treat to wade through that nonsense. Yeah. This was at the Gran Sasso experiment in northern Italy.
Totally different than what I was talking about then.
Yep, 100%. I mean, it's close, you know, a couple miles.
Not really.
Miles off. It's in the Alps. You know, got the right mountain range. There's a nuclear reactor on one side of a mountain, and then they bored a tunnel through it, through the mountain, and then there's a detector on the other side. And the nuclear reactor is doing its normal nuclear reactor stuff. And what they're hunting for in this experiment is neutrinos. These tiny, tiny little particles have just a little bit of mass, super ghostly, like little ninja particles, absolutely flood everywhere, but they hardly interact with normal matter. They're generated in nuclear reactions. And this research group was studying some neutrinos, experiments, results from this nuclear reactor. And they found that the neutrinos were traveling faster than the speed of light. And when this happened, the collaboration that was in charge of this experiment, they talked about these results, you know, they poured it over. Half the collaboration said, look, we're just screwing something up. Let's just move on with our lives. And then half said, no, I think, you know, we checked, we looked, we checked underneath all the rocks, like we did our homework, like as far as we can tell, and it's our responsibility to report it to the community that something weird is going on. And so the collaboration splits. Only half the collaboration wrote the paper. And they wrote the paper. And the paper itself had all the usual caveats of like, you know, we don't understand what's going on. Here's all the stuff we tried, blah, 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 blah. But of course, the news media went wild. And of course, they did a bunch of interviews. And it's all like neutrinos travel faster than the speed of light. Like all of physics is broken. 3 months later, or a few months later, they were going back over the experimental apparatus, and they found that a cable in the back wasn't plugged in all the way.
Right.
And it was causing a lag in one of the signals.
I remember.
And they plugged it all the way in, and neutrinos didn't travel faster than the speed of light anymore.
I remember.
Yeah.
Oh, yeah. Yikes. Whoops. Yeah.
Yeah. Oopsies.
So you had one job,
that
Steve.
Was rough. That was rough.
Yeah. That was
because when it came out, I'm just like, no, of course not. Like they did something wrong. And then still to this day, they're like, what about them neutrino things?
Nope. So let's see. There's so many good questions coming in. I thought we did answer that one that Bad Joker asked. Ask him if antimatter has repulsive gravity. Nobody asked that yet.
Nobody. Finality. Just all the hand gestures that mean no.
At what speed is the universe expanding, and what happens if we travel faster than the expansion speed in a straight line?
All right. Our universe is expanding at a rate of... Are you ready for some of the worst astronomy jargon in the world?
Oh, God, yes.
Yeah, here we go. But they asked.
I know.
It's expanding at roughly 70 kilometers per second per megaparsec.
Everybody's eyes.
So I'm assuming the kilometers per second is pretty okay for everyone. Okay. Megaparsec, a parsec is around 4 light years. So a megaparsec is around 4 million light years. And this term, 70 kilometers per second per megaparsec, means that if you go out 1 megaparsec, then that galaxy is receding away from you at 70 kilometers per second. If you double that and you go out to 140 megaparsec, if you double that and go out to 2 megaparsec, then that galaxy is receding at 140 kilometers per second. If you double that to 4 megaparsec, then that galaxy is going 280 kilometers per second. The farther a galaxy is away from us, the faster it appears to recede. So if you can travel faster than 70 kilometers per second, you can catch up with a receding galaxy. But there is a point where this keeps adding up, 70 plus 70 plus 70 plus 70 plus 70 plus 70 plus 70. There's a point where the speed is faster than the speed of light. And that happens that's about 13 billion light years away. So if you see a galaxy about 13 billion light years away is receding away from us faster than the speed of light, you can get in your rocket ship. You will never, ever catch up to that galaxy. Ever. Because the expansion of the universe is too fast.
So Mythic just goes, you can catch up but never catch?
You can never catch up.
Never catch up.
To that. You can never, if a galaxy is more than 13 billion light years away, you will never, ever, ever catch up to it.
Yeah, make sure someone just says, Philip says solution, drink Red Bull and have a power bar. I would suggest both of those.
Oh, that's a good combo. That's a good combo.
And have a power bar.
Maybe a Camelback.
Yeah, or at least 2.
It's a marathon, not a sprint.
Okay, so I see your questions, guys, at the bottom there, but I want to... there was somebody asked about if you were traveling at the speed of light. Oh, there it is, KSP. If you were moving at the speed of light and you moved your hand forward, would your hand be faster than light?
Well, you can't.
Do you want to just say no? So we can't travel at the speed of light.
You can't travel at the speed of light. Light can travel at the speed of light. If you're traveling close to the speed of light, I should say this. You can't travel at the speed of light anyway. In your reference frame, no matter how fast you're traveling, like if you're on a train and you're going 200 miles an hour, you're on one of them fancy maglev trains. And you wave your hand in front of your face, according to you, your hand is only moving a couple miles per hour. Right? Because you're watching it. You can see it. Look at that. And that's it, because that's in your reference frame.
Right. That's your frame of reference. Yeah.
Relativity matters, folks.
Is it observable that the universe is expanding at the same rate no matter what axis we are looking at? Yeah. Wherever your vantage point is, it's going to appear to be expanding. Yeah, it doesn't matter.
Our universe is homogeneous and isotropic.
Ooh, those
which means
are fancy
it's
words.
roughly the same. Great words. It's roughly the same from place to place, like milk. And it's roughly the same from direction to direction. So it is expanding uniformly in all directions.
Yes. Let's see. So our measurements aren't wrong at all. I don't know if he's talking about the expansion of space. I'm guessing that's what you were talking about, Dragon?
All measurements are wrong all the time.
Why is the radius of the observable universe larger than 13 billion?
Right, so our universe is 13.8 billion years old, but the radius of the observable universe is 42 billion light years, and that's because the expansion of the universe is faster than the speed of light.
Can you explain the curvature of the universe and why it matters and how we can measure it? how we could measure it.
Yes, so the curvature of the universe, there are some great mathematical definitions of the word curvature. My favorite definition, and the one that's best to use, is what happens to parallel lines. So if I take two beams of light and they start off perfectly parallel and they shoot off, what happens? If you're on a flat piece of paper, they'll just stay parallel forever. If they're on a curved surface, like the surface of the Earth, and you start off with, two laser beams pointing north, they're parallel, but then they eventually intersect at the North Pole. So that's how you can tell the Earth is curved, because parallel lines don't always stay parallel. So you can imagine in our universe, shooting laser beams out into space and asking at big scales, like ignoring galaxies and black holes and all this small stuff, at big scales, do parallel beams of light stay parallel, or do they come together, or do they separate? This is important because the curvature of the universe tells us what the universe is made of. That's general relativity. If you have stuff, you bend space-time. If the universe has stuff, the universe gets bent. So by measuring the geometry of the universe, we can measure the stuff in the universe. It's the exact same question. And we checked this, and our universe is flat. To less than 1%. Is very, very flat.
Flat shaming the universe. Okay, so
flat is great. Flat is great.
Said no one ever.
All shapes are welcome. We just happen to have flat.
So does Higgs boson give particles their mass?
The Higgs boson, when you look at something like the electron and you're wondering, hey, the electron has a mass. Why? Just why? Why should the electron have mass? Or why should a top quark have mass? Why should a neutrino have mass? Just why? Like,
why?
Who's in charge of that?
Why?
And we discovered that there is a field that permeates all of space-time, that soaks the universe like olive oil. And this field we call the Higgs field. It does some other important jobs in physics that I won't get into. But one of its side benefits is that it talks to things like electrons. Electrons see the Higgs field, and they interact with it. They talk with it. As they move around, as they do this thing, they talk and interact with the Higgs field. That interaction between an electron and the Higgs field is the mass of the electron. That connection point, that dialogue is the connection, is the mass. What we call the mass of the electron is really it talking to the Higgs field that permeates all of space.
I think that was great. And Largo, thank you. No. Sorry, I do have alerts turned off, guys, just so you know when I have a guest on. I feel bad because I don't want people thinking I'm trying to be mean.
Well, you are mean.
I know, so rude. Beardo, I can answer that one. If the universe is expanding and everything's getting further apart, then why is Andromeda coming closer? Can also other galaxies come our way? We're in that local group where we're kind of sharing the same, I guess you could say, I like saying galactic sync.
I love it.
Yeah.
That's great.
Picture our little group as all being in the same sink.
We got a little bathtub to us.
Yeah.
To ourselves.
Yeah. So that's why. If it were further away, then that's where you start seeing that. So the universe is traveling faster than the speed of light. I thought nothing could. The expansion of the universe.
Right. So things like velocity and speed of light and special relativity, that's all local physics. You will never ever see a rocket ship blast by you faster than the speed of light. But something on the opposite side of the universe can do whatever it wants.
I am seeing. Why is it that you can measure the speed of an atom, but not its position, or you can measure the position but not its speed?
So this gets into really, really funky quantum mechanics about the fundamental fuzziness and uncertainty in our universe.
Mm-hmm.
And one of the fundamental uncertainties and fuzzinesses in the universe is that certain kinds of observations can't always go together as well as you'd like. So if you want to measure the position and the momentum of a particle, you can get a little bit of both. You can get a lot of one, like a lot of detailed knowledge of one and sacrifice some knowledge of the other, or vice versa. But you can't get detailed knowledge of both. This is called the Heisenberg uncertainty principle. And there's actually quite a few uncertainty principles floating around, but all based in the same idea, which is nature fundamentally prevents us from knowing everything we'd like to know.
So in the same sync, so we're going down the drain with Andromeda. Yeah, we're gonna collide with Andromeda, or Andromeda's gonna collide with us, whichever way you want to say that, whichever one makes you feel a little bit better about yourself. You can choose, right? At this point.
Yeah.
You know, about 5 billion years.
We're mixing together, don't worry.
Yep. So light travels faster in other galaxies?
No, other galaxies, some distant galaxies are being carried away from us faster than the speed of light.
But what if, and if is
what if?
Yeah, the but is capitalized, and I think Harmer did this intentionally. I don't think he didn't just derp everywhere. So, but what if we traveled faster than the expansion?
What if we traveled faster than the expansion, man?
What's on the other side? What's your opinions, man?
What's up, man? What if you could stick your hand through the wall of the universe?
That'd be far out, dude.
Totally far out. So check this out. Like, we have our observable bubble of the universe that's 92 billion light years across. And all the galaxies are receding away from it. If you were to travel to another galaxy, then from your vantage point, you would be surrounded by a bubble 92 billion light years across with all the galaxies receding away from you. If you picked a random galaxy in that bubble and hopped over to it, or magically transported whatever, got over to it, then from that vantage point, you would be inside of a bubble that's 92 billion light years across, and all the galaxies would be receding away from you. Pick another, like this goes on and on and on and on. Our universe has no edge. Our observable bubble has an edge because there's a limit to what we can see, but the actual universe has no edge.
And soon, and this is the depressing thing, is that our observable bubble is getting smaller and smaller.
Yes, because galaxies are getting pulled away from us faster than the speed of light, which means despite the fact that our universe is expanding, the limit of what we can see actually shrinks as stuff gets pulled away from it. And in the far, far, far future, like 100 trillion years or whatever. Oh, no, not that long, like 100 billion years. It's just our local group. It's just our bathtub. That's all we got.
Yeah. Does the expansion of space-time have any influence on anything like matter or certain universal constants? Ooh.
As far as we can tell, the constants of nature really are constant, have been constant for 13.8 billion years, are constant throughout the universe. It's an active question because it'd be really, really cool if we can poke a hole in one of these constants and learn some new physics. But as far as we can tell, constant really does mean constant.
Yeah. And yeah, Dukes, it does sound lonely. We're still in a nice little time where we can still see things.
You better learn to love yourself because it's pretty lonely out there.
It is, and it'll just get lonelier and lonelier.
Yeah.
Do we know where the center of the universe is? You're the center of the universe, Dr. Paul. But I'm also the center of the universe.
Exactly.
How?
We're all the center because the universe has no edge and it has no center. The Big Bang happened everywhere simultaneously. Everybody has their own vantage point. They're surrounded by a bubble that's 92 billion light years across, with them at the center, with all galaxies receding away from them. But if you go to any other point in the universe, you get the exact same perspective. So nobody is the center of the universe, but everyone's the center of their universe.
Has the speed of light always been constant? Are there theories that stipulate that it's changed from the Big Bang hold water?
There are ideas, hypothetical ideas, where the speed of light has changed, especially in the early days of the universe. As far as we can tell, it stayed constant.
Sorry, these comments are great. Have we witnessed a galaxy vanishing out of our sight yet?
So the time scale, like to actually watch a galaxy vanish, you're talking
pretty
millions, hundreds of millions of years. We do see galaxies that are barely on the edge of our detectability.
And that's what's really cool about that is those are babies, because we're seeing them. We're seeing baby galaxies, even though those galaxies might not even, they're probably not there at all.
Well, they've certainly
they've
gone
probably
away
moved
by now.
Yeah.
But
maybe merged with other ones. But
yeah, the farther you go out in space, the further back in time you go.
So you see baby photos when you look really far away. If the universe is expanding and galaxies are spreading apart, so the universe cannot end due to heat death. Oh, we're talking about all these different, the big freeze, heat death, big crunch.
So heat death is like the worst name.
Yeah.
It should be called death of heat. The big freeze is synonymous with the heat death. It's the loss of heat. As the universe expands and cools and temperature differences approach zero and the global temperature approaches absolute zero, that is the heat death of the universe. As far as we can tell, that is our fate.
Yep. Although Dr. Katie Mack's writing a book about all the ways that the universe can end. She's still working on it.
Or if you're eager,
I have mine right over here, but I don't want.
It's so over there. You can buy a book that's already in print and available in bookstores nationwide. And you can go to chapter 13, The Fall of Light. Are you still reaching for it?
No, I got it. We're fine. Let's go, champ.
Okay. Or you can go to chapter 14, The Long Winter.
I got it. The Long Winter. We'll have to do another book reading night sometime.
That'd be fun. That'd be fun. I don't have a Christmas tree anymore, but
we can maybe make something really cheesy about Valentine's Day, talking about our love of the universe.
Oh, there we go.
Yeah.
Yeah, we'll do holiday specials.
Yes, only holiday specials. That's right. Let's see. There was another one. Planck constant was recently ad hoc set to be a fixed value, and it's gone. Hold on. And doesn't that make us unable to test if the constants are actually staying the same or not?
So we have some very, very detailed images and observations of the early universe. Not super early universe, like we have them from when the universe was around 400,000 years old. And you can start playing around with physics. Like, okay, maybe the Planck constant is different back then, or maybe it changes, or maybe the speed of light. And you just play with these numbers, and then you run all the physics, and you get different observations that you can compare against the observations that you do have and see what happens.
Why is my copy so much bigger than Dr. Paul's?
It's not the size of the copy that matters.
Size of the human.
Power of the words. No, this is my advanced reader copy. So this was just the uncorrected proof the publisher sent to me. It's not the hardcover.
Can our galaxy be a part of another galaxy? Our galaxy is merging with other mini galaxies as we speak right now. Happens all the time.
All the time.
All the time. And
All the
will
time.
continue to happen.
Until it doesn't.
Until it doesn't, right. If the electron's interaction with the Higgs field gives it mass, what is the electron that we are referring to? Is it another field? Ooh.
Ooh. Very insightful. So I said the electron interacts with the Higgs field. That interaction is the mass of the electron. You are correct, sir or madam. The electron is really its own field. In fact, every fundamental particle is its own field that permeates and soaks all of space-time. And all these fields sit on top of each other, and all these fields constantly interact with each other in very interesting ways. And sometimes the fields will get a lot of energy in one spot, a lot of vibration, a lot of energy, a lot of localized energy. And that's something we call a particle. This is the picture that we call quantum field theory. This is our fundamental picture of reality as provided by quantum mechanics, that our universe is filled with fields, and what we call particles are really just little pinches of those fields that exist temporarily and go travel and go do something.
You can be really cool and just say QT or QFT. You can be really cool if you want to.
For truth.
Yeah, just be like, yeah, you know
Also
about
quantum
some,
field.
yeah, some QFT, you know.
Yeah, you know me.
If everywhere is the center of the universe for the observer, does that not kind of disprove the Big Bang theory?
It does not kind of disprove, which means it proves the Big Bang. The Big Bang was not a point in space like over there that blew up. The Big Bang is a point in time. The Big Bang happens simultaneously everywhere in the universe.
Right.
13.8 billion years ago.
So it's a matter of when, not where.
Exactly. Because it was everywhere.
Yeah. So, because I think a lot of people say, like, or is my perception of it being wrong? He even said, understanding that everything originated out of a micro point. And yeah.
Yeah.
And wait, there's another question. I might have missed it. Michael, did I miss one of yours? There was a question about negative energy, maybe? I'm trying my best. There's a lot of questions.
Man, they're slamming today.
I know. So it was the biggest bang. The Big Bang.
Yes. The only bang.
That's why I love quantum physics. Fascinating. I want to spend some time thoroughly understanding it. Yeah, it with air quotes for sure. So does the Big Bang look the same from anywhere in the universe?
Yes. I mean, there'll be little differences. Like if you go to a random part of the whole entire universe, you'll have a different pattern of galaxies. You'll have a different cosmic web. You'll have a different cosmic microwave background, but the statistics of it will remain the same.
Oh, I think we discussed that last time, didn't we? Or like a few times most recently.
Just watch the tape.
It's all on the YouTubes. Now my brain hurts. I know. I was just about to say, hey, thanks, Dr. Paul, for, I've been live for a solid hour and a half. And I think everybody is their brains are just.
We're tired. We're spent.
Oh, wait, let's see. So something that I've wondered, say there's no space outside the universe. Does it mean the self-contained universe is getting more dense with space instead of growing, since then it can't grow into anything?
By definition, the universe is all there is. All the things are the universe. The universe has no edge, has no center. There is no such thing as outside the universe, because the universe is all the things.
All the stuff.
All the things.
We need a beer to wake up now. And smoked Gouda.
Yes.
No, Fenring, that's fine. I missed some. So if people are asking questions, I'm not thank you for actually posting it again. Why is inertial mass, because I thought that was such a great one, why is inertial mass the same as gravitational mass?
So we don't know. This was a question that really bugged Einstein. It actually bugged Newton, but he's like, whatever, I can't figure out all the question. Einstein picked it up. It really bugged him. He didn't know why inertial mass was the same as gravitational mass. So he just made it a fundamental rule of the universe. He just said, okay, we're just going to call it like, inertial mass is gravitational mass. From that statement flows all of general relativity. That is how you get to general relativity, is from that realization.
Okay. Time Lord. So I think, guys, we have I can take 2 or 3 more. Probably 3? 3? Is that okay? 3? There's 3 really good ones. Okay. So, if we know dark matter energy is stationary, or do we know if dark matter energy is stationary, or is it moving with our expansions, galaxies? We believe dark energy is kind of what's driving the expansion from what we think, right?
Yes. Dark energy is the name we give to the accelerated expansion. We do have some very, very hypothetical models where it's another field that soaks all of space-time and it's doing its own thing. Dark matter certainly moves around. It flows, it collects, it disperses, it moves. It's on the move.
Mm-hmm. It acts like matter for what we know now.
Yes.
We just can't see it, hence dark matter. So everybody's like, wait. No multiverse? Because you just talked about,
Right. There could be, we have this conception of the multiverse, which is different universes with different fundamental constants, different sets of forces and particles, different, just different physics. Those concepts are very hypothetical, and so I'll leave it there.
Okay, last question. If the universe is infinite, how did they calculate the total mass of the universe, which led to the theory of dark matter? What a question.
If our universe could be infinite, we actually don't know. What we care about, though, is not when we quote the total amount of stuff in the universe, we're quoting the total amount of stuff in our observable bubble. What we really care about, the number we actually care about, is the density of this stuff. That's what we care about. How much stuff is there per cubic yard? That's our number. That's the one we care about.
And guys, we have the All-Stars party. It's in the background right here. I'm going to be tweeting this out this week too, to bring more awareness to this. If you want to hang out with this cool guy right here and ask these questions the whole entire trip, I'm going to say do it.
Nonstop. It's hilarious.
And I'll be there too.
And you'll be there.
And I'll be there. And also Dr. Pamela will be there. And Fraser will be there. And John Michael Gaudier, which I actually like a lot of his stuff. I've been looking at some of his stuff.
Super cool guy.
Yeah.
Super cool guy.
Yeah. So there's the link there. We need more people to make this happen. So I will be tweeting about this and asking for all the retweets.
All the retweets.
On the tweeters. So, well, thank you so much for...
This was tons of fun.
Yeah, thanks for... that was probably the most questions that we've ever had. I think we just broke a record.
Whew.
Yeah. So now we're just going to go and just watch something, and we're all going to tell each other we're fine.
Take another nap. I thought I only needed one nap today. I guess not.
I'm going to go get 3 more cups of coffee. I'll be fine.
Okay, I'll be fine.
All right. Well, I'll see you next Tuesday. Maybe we'll see.
We'll see. One week at a time.
All right. Talk to you soon.
Take it easy.
All right. Bye.